Hello everybody, so today I will talk about the system design of Dropbox. So this is my second take of this system design question, but I will do it, practice it, repeat, again and again. Yeah. So I will start with the functional requirement. So maybe I should start with the explanation of the Dropbox. So Dropbox is a kind of the file storage service. So user can upload the file to the Dropbox, and also user can download the file from Dropbox. But the biggest, feature is that the files are synced, or I should say uploaded and downloaded automatically in the background. So I just have to specify which folder should be synced. Like, let's say we'd like to sync the folder project in my local machine. And I have to specify it. And then the files I added, the file I insert into that folder is synced, updated to the server, cloud. And if there is someone who uploads the file to the cloud, that file is automatically synced into the local machine in the project folder. So this is Dropbox. So for the functional requirement, I would say user can upload a file, and also user can download a file. And as I said, they should be synchronized. So files are synced across devices. So I can say these are three functional requirements. Now I will talk about the non-functional requirements. So I will start with the CAP theorem. So in CAP theorem, C is consistency, strong consistency, and A is availability, and P is partition tolerance. And because we're developing the distributed system, first P, which is partition tolerance, is the must. And we can satisfy two of three, so I have to choose from consistency or availability. So just to be clear, if we don't guarantee the partition tolerance, what happens is that if there is a network loss between the servers, the whole system goes down, uncontrollable. And obviously it's not acceptable, so I have to choose partition tolerance at least every time. And okay, so consistency versus availability. So I will explain the trade-off between them. So if I choose the availability, okay, so let me say, firstly, I will say the, definition. So consistency, strong consistency, I can think of this as if there is a kind of update, right, in the data from some process, any other process can read the latest data, including the latest write. So that's the strong consistency. So what happens is that if I'd like to guarantee the strong consistency, the data has to be always at one place. Otherwise, let's say there is a data replica somewhere, and only the master data is updated by the client. And if some other client tries to read from the replica data. So in this case, let's say user would like to copy the data. The data in the master has to be duplicated, or I should say synced into the replica. And if there's a network loss between these, the latest write is not propagated to the replica data. This means that we cannot guarantee the strong consistency. But instead of that, what we can do is, because the data is now living as two duplicated, you know, entities, even if either of them dies, the other is available. So this means that availability is now in our hand. So in this way, we have to guarantee, we can guarantee each of them. And so in this case, we can rephrase this consistency versus availability discussion as, let's say user uploads a file and the other user, he should read the latest file always, or, and if it is not possible, user should not be able to get outdated file. Or if we choose availability, users always can download the file, but it may be a bit outdated. So when I think of two, options from the user's perspective, definitely we should go with availability. Even if the file is a bit outdated, it's much better for user to be able to download the file. So I go with this. Okay. Next, I would say durability. So what I mean to say is the file stored in the S3. Oh, I said S3, yeah. But the file stored in the server side should always be durable. So the file should never be lost. It's just a kind of business, reliability we should always, satisfy. So durability is must. And also, I'd say low latency. So this is a bit tricky here because the file can be maybe 1 gigabyte, 10 gigabyte, which is so big. So if the file is so big, I cannot say, the file size varies, so I cannot guarantee the exact number, like 500 megabytes or something like that. So I would hand wave like as early as possible, as fast as possible. Sorry, as small as possible. Okay, next, I would choose the. Okay, now I will talk about the scalability. Oh, sorry, let me say for torrents first. So it is possible that user would like to upload or download 1 gigabyte of file or maybe 10 gigabyte. And it is possible that almost at the end of the uploading, there is a kind of network failure or maybe server goes down. In that case, I want to avoid the user uploads the file from scratch or maybe downloads from scratch because it takes so much time again, and also it uses the network resource or maybe the server resource in the server side. So I don't want to accept it. So for torrents here, I'd like to make it possible that user can resume the upload from where it failed. So resumable upload. And the last one is scalability. So for this one, I will put the number from my node. Okay, so 100 million daily active users, and each file can be up to 50 gigabyte. Okay, so this is the non-functional requirement. Okay, so from here, I will talk about the core entities. So core entity is like the DB table. Yeah, so and here I don't list the attributes. I will talk about it later when I necessary. So core entities, I can say user is there, obviously, and there is a folder. This is the folder kind of entity which user specifies in the local machine. and synced in the server side. Obviously, we have to keep track of this entity on this end. And we need file. And file has two things. File itself, the file content, and file metadata. So file metadata is like the file size, maybe file format, when it was uploaded, when it was downloaded, maybe, and when who created that file or something like that. Yep, maybe, and I need device. So because user has many devices, maybe we have to, distinguish them. Okay, so these are the core entities. So from here, I will talk about the API design. So one thing I'd like to clarify, maybe two things I have to clarify here. So number one, about the specification. So I said user can upload the file. And the thing I can think of, the scenario which is possible is that there are two users who'd like to update the same file. In that case, what should I do? And here in this design, I take the Rust update wins policy. So if there are two users who tries to update the same file, the later user, the file content is updated with the latter user's upload. Okay, so I will write it here. Last update win. Okay. And also, what should I say? Oh, and one more thing. So here in this design, I will think of the upload, newly creating the file and updating the file content. I don't think about file deletion for the simplicity, but I will think about it later if necessary. And another thing is, okay, so maybe this is the most important thing about the system design. So the file is so big, maybe it can be 10 gigabytes. So I will save the data file in the blob storage because blob storage is created for this purpose. We can store it in the database, like PostgreSQL. It is possible, but our DB is not suited for that. Okay. And also I can say if we use the cloud storage, definitely S3 is cheaper if I save the same file. Okay. And that being said, so now I think of the API design, but when I think that the file should be stored in the S3, when user uploads the file, I want the user to upload the file directly from their front-end device to the S3. We don't want a file to go through our backend because it takes so much resource. So that being said, I will use the S3 pre-signed URL to upload the file and download the file. So what happens is that firstly, user makes the file metadata in our server side. And then our server side hits S3 to get the pre-signed URL and returns it to the user. And now in the second hop, user uploads the file to S3 directly from the pre-signed URL. So that's the design I will use here. And same for download. If user would like to download the file, firstly he gets the download URL of S3 from our server, and then user directly downloads the file from S3. So that's what I will design here. So number one, create file metadata API. So user have to specify folder ID and then try to create a file. So this is it. And because we need the user to specify the path of the file, we need this. Okay. And obviously we need the user to specify the header, and let's say token. This is used for the authentication, and now server side can know which user is uploading by getting the user ID. So with this, the file metadata is created, and we need to return pre-signed URL. So this is create file metadata API. Secondly, we need the upload file API. So here I use the pre-signed URL. Okay, and good. So next, sorry, and this returns maybe 200 success status that the file was uploaded. Number three, user can download the file. So same for here. User firstly get file metadata, maybe partially. We just need file ID here. Okay, and again, we need the authentication to know which user is trying to do it. Then we should return maybe file metadata. The reason why I return the whole file metadata is maybe in the future user would like to know the maybe information of the file, like file size. So we include file metadata in the response body. Next is user can download the file, and they have the pre-signed URL, so get file content. So they specify pre-signed URL, and they get file content. Okay, so this is the download file API. Okay, so now I will talk about the high-level design. So I will implement each API one by one. Okay, so firstly, users should be able to upload the file. So I will implement the create file metadata API. So there is a user, and maybe I should say user, maybe device. And there is a folder inside of this device. This is a specific folder which is synced into the how should I say, server side. Okay, so there is a front end, or maybe I should say backend agent application which is running on the device. So this device makes the request to our backend, and I will use the distributed system microservices here So firstly, I put the API gateway here. The reason why I go with the microservices is I would like to work each, maybe uploading, downloading, working separately. I want to avoid that when file upload API dies, or maybe if there is a problem on that, like memory leak, I don't want the download API to fail. So I separate the servers. So that's why I use the microservice architecture here. Yeah, of course, there are so many reasons that I choose over microservices, but yeah, like maybe for the ownership of the service or something like that. But yeah, anyway, I will go with the microservices architecture. So now I'm thinking of the uploading file. I put the upload service and we need to create the file metadata. So I put it in the database. So the basic flow is when user tries to upload the file, it hit the upload service and then it hit create or maybe update metadata. And what should be stored here is file metadata, path, and what else? Maybe path can be identifier, they can be primary key, and I'd like to know who updated this file and updated at timestamp. Aside from that, maybe folder ID. So we need the folder data also. Maybe like group ID or something. I don't know. Yeah. I don't talk about this creating folder here. I start with uploading the file. So in this way, the file metadata is created. Oh, and also we need S3 object key. This means where it was stored, and also S3 upload status. This is a kind of state machine, like uploading and uploaded. Good. Okay, so now the file metadata is created, and as I've written here, we have to return the pre-signed URL. So we have to issue the pre-signed URL. So this upload service gets the pre-signed URL from the S3 and return it to the user. So S3's object key, it can be just simple as the file path with maybe the namespace, group ID, and folder ID. So now the record is created and also pre-signed URL is created. So we can return the pre-signed URL to the user. But one thing I have to think is the kind of atomicity. So I want to avoid that the either of the data is created, but then it fails. So what I can do here is upload service firstly creates the pre-signed URL in S3 from S3, and if he can get it, then it creates the file metadata and then return the pre-signed URL to the user device. So if pre-signed URL issuing succeeded, but creating the metadata fails, what happens is that in the S3, a kind of zombie object is created, which is never be uploaded. So what we can do for this is maybe we can create another process, kind of cron job, and that cron job checks S3 all the files. And if there is a file which hasn't uploaded, or maybe the upload failed, and it took more than maybe 1 day, it should be deleted by the cron job. So that's what I can do. Okay, so that being said, I will talk about the second API, upload file. So this is quite simple. The device background job just has to upload the file with present URL. So actually, we can use the S3's multi-path upload feature to realize the resumable upload. Yeah, but I will talk about it later. Okay, so this is about the upload API. Next, number 3, get file metadata. So quite similar thing happens. So when user makes the request to fetch the file, the request is sent to download service. As I said before, I separate these services because even if there is an issue in either of them, especially in the upload service, I want the download feature to keep working. So now request goes here to this server, and this server fetches file metadata and return it to the user. Okay, and also this this download service has to get the pre-signed URL for download, then return it to the user. So this is number 3, and then for API number 4, download, the device can download the file from this pre-signed URL. Just to be clear, the reason why I use pre-signed URL is I want the URL to be temporary. So if the URL doesn't change for a long time, it is possible that the pre-signed URL is leaked and some other user who are not in the group can download the file, or maybe they can upload the file, big file to S3 for their own purpose, or maybe malicious purpose. So I want to avoid it. So I want this URL to be expire after some period. So that's why we use the pre-signed URL. Okay, now I talked about these 4 APIs, but actually there is one thing which is missing in the function requirement. That is, user files are synced across devices automatically. Or maybe I should say in the background. So for this purpose, we need the background process application. Maybe I should say agent, which uploads the file or downloads the file. So this keeps working, and I have to think how new file is uploaded to the backend. So I mean, this background application process has to be so smart. So how he can know if the file is created or updated in the folder? So we can use the OS system call watch. So the background application calls the OS system call to watch the folder. Then if there is an update in the file, in the folder, always notifies the background application that there was a change. So now this background application checks the local file and upload the new, updated file to the S3. So that's what happens. And now the second problem is how he can download the file. So here, I think I can use the short polling. So what I mean to say is this background application makes the request to our backend with Rust sync timestamp. So background application key tracks Rust synced out timestamp, and this application makes the request to get the list of files which were uploaded from the last time. Or maybe we can return OZ, maybe. Okay, yeah, I will simplify. So server side returns the list of uploaded files, and now this device can download each file, maybe concurrently. So the thing I have to do is, firstly, I need to get updated files API. And the backend specifies the last synced at and also folder ID. Maybe we can include it in the folder ID here, and now the backend process can know which files are uploaded. Okay, and now the background application makes a request to get file metadata, and yeah, get the S3 download URL and download the file directory from S3. Okay, good. Maybe I should talk about other options here. So if we'd like to know the file update in real time, we can use maybe WebSocket. So I will compare why I choose short polling rather than WebSocket. So maybe I can say this is a kind of trade-off between the complexity versus user experience. So user experience wise, sooner is better actually. So with WebSocket, we can return the file ID update maybe in sub-seconds. But this comes with the very complexity. And most of the users, it doesn't have to be that fast. Maybe update every 1 minute is good enough. And also I can say, if the user opens a folder very frequently or writes something very frequently, we can do the short polling frequency. I mean, we can make it more frequent. So in that way, we can control it. So maybe there is an option that he really want to use it like the real time thinking. Maybe we can kind of provide the service, right? I mean, premium plan, like real time update. But in that case, I think it more like the Google Doc or file sharing service rather than file syncing service. Yeah. And if the user really has to, update the file so often, the specification last update wins doesn't work. So we have to think of the kind of file, merging approach for multiple writes. So in that sense, I think short polling is more appropriate for our scenario. So I went go with the short polling. But yeah, according to the user's requirement, maybe we can use the WebSocket. But basically, I would push back. Okay. Good. So now I talked about high level design. So in the next video, I will talk about the more deep dive, like, or I should say, I will talk about the non-functional requirements. Okay, so that being said, I finished my today's practice. Thank you so much. Bye.